करने के लिए हमने राजकीय पॉलिटेक्निक झांसी से श्री सुनील कुमार व्याख्याता इलेक्ट्रॉनिक्स अभियंत्रण को आमंत्रित किया था और वो हमारे साथ हैं इस समय। और सर का 9 से 10 वर्षों का तो इस विभाग का ही अनुभव है। इसके अतिरिक्त जो भी इंट्रोडक्शन है वो सुनील कुमार सर स्वयं देंगे। सो स्वागत है सर, प्लीज।
थैंक यू। हेलो, नमस्कार, a warm welcome to everyone at Electronic Media and Resource Center, IIT Kanpur. So today we have this operational amplifier lecture here, and I am Sunil Kumar, a faculty member in Electronics Department from Government Polytechnic Jhansi, Department of Technical Education, Uttar Pradesh. So in this particular lecture, we will cover the module Unit 1 and Unit 2 of linear integrated circuits. Basically, this subject is related to Diploma in Polytechnic second year students. They are learning this subject, and operational amplifier is one of the topic of this subject. So first, we will discuss about the syllabus of this subject, that is as per Board of Technical Education, Uttar Pradesh. So here we are able to see that we have total of 5 modules in which we are going to cover module 1 and module 2. These 2 modules we are going to cover in this online e-lecture. So this is the part operational amplifier where we are going to study its symbol, pin diagram, its properties, different characteristics, and after that we will discuss the application of operational amplifier. Application means all kind of linear application that we are going to discuss here. Linear application means summing, scaling, averaging, subtractor, integrator. So we will make the circuit diagram of all these circuits, and after that we will do the analysis. So we are going to cover this module 1 and module 2. So these are the different modules, module 3 and module 4, that we will learn after these lectures. So introduction of operational amplifier. So this is the first question, that what is operational amplifier? So operational amplifier is basically in short form we are writing it as op-amp. In short form we are saying it operational amplifier, op-amp. So this is operational. This we can write as operational, and this is the amplifier. This is amplifier. Why do we call it operational? Because operational amplifier can perform some linear operation. Basic linear operations we can perform through op-amp. Means it can perform linear operations. Like addition, that we can conclude with adder, subtraction, we can do integration also, and opposite of integration, that is differentiation. So these kind of operation we can perform through this operational amplifier. That's why this is known as operation. And second one is amplifier. Amplifier means we are getting output always greater than input. Whatever voltage we have applied at the input of operational amplifier, we will get a high output. Output is always greater than input. That means we will introduce a term here. This is called as gain. Gain can be written as output voltage, V output, divided by V input. V input is the voltage that is applied at the input of operational amplifier. Because of this, we are calling this op-amp as operational amplifier. And we remember, it can amplify signal ranging from 0 Hertz to 1 megahertz. This is the practically it can amplify signal from 0 Hertz to 1 megahertz. If we talk about the ideal operational amplifier, then there is no range, there is no such foundations for ideal amplifier. So here we will discuss the properties of ideal op-amp also. So it is available in market. If we want to purchase this, so this is available in market in the form of IC 741. It is integrated form. IC is 741. This is the op-amp chip. We can call it as chip in integrated circuit form. Operational amplifier is available as 741. So we can discuss its pin diagram also. This is an IC of 8 pin. We can draw its pin diagram. This is the pin diagram of 741. So this is having 8 pins. So we can write it as 1, 2, then 3, 4. Here we have 5, 6, 7, and 8. Whenever we see any kind of IC, there is a cut at the top of the surface, and we have a dot here. So just a side pin of dot is known as 1. So this is the pin diagram. So here these two terminals, 2 and 3, these two terminals are used for input. These two terminals are used for inputs. Then we have 7 number pin. 7 is used for positive DC supply. We need to apply some DC supply in operational amplifiers integrated circuit so that it can operate. Similarly, in 4 number pin, we are applying minus VCC. This is generally grounded. And we have this 8 number pin, that is basically not connected pin. We don't have any kind of use of this pin. This is not connected pin. This is only for the purpose of making symmetry. That's why this 8 number pin is useless. This is not connected pin. And these 1 and 5 number pins are known as, these 5 and 1 number pin are known as offset null. That is very important to understand that what is offset null, that we will discuss later on as we discuss about the characteristics of ideal operational amplifier. So this is the pin diagram. Operational amplifier is available in integrated circuit form, and the IC name is 741, where we have these kind of pins. 1 and 5 are offset null. Here this 2 number pin is known as inverting terminal. This is called as the inverting terminal. And we have this 3 number pin that is known as, this is known as non-inverting terminal. This is known as non-inverting terminal. Suppose we have a question that how this operational amplifier is differing from other amplifiers. Generally, if we talk about amplifiers, then we must have an input and we are getting some kind of output. But in operational amplifier, we always get an output because of the difference of the input signals. Here we have 2 inputs. One is applied at 2nd number pin, that is known as inverting terminal. One is at 3rd number pin, that is known as non-inverting terminal. So operational amplifier is going to amplify the difference of these 2 input terminals. The voltage applied at these 2 terminals, the operational amplifier will amplify the difference of these voltages. So this is the pin diagram. Similarly, we can see the symbol of this operational amplifier. We can see the symbol of operational amplifier, and we remember linear integrated circuit basically processes the analog signal for a continuous range. An operational amplifier is the best example of linear integrated circuit that is widely used in electronics engineering. We can do filtering, we can amplify, signal conditioning. There are lots of applications that we can perform through operational amplifier, and we will discuss later on what kind of linear operations that we can perform by using operational amplifier. So this is the symbol. So it is like triangle. This is a triangle. We are making the symbol of op-amp. So we have this triangle here mentioning as minus, this is plus. What is the meaning of this minus, that we will discuss later. And this is the 2nd number pin. This one is 3rd number pin. Then we have output is at 6 number pin. Output is at 6 number pin. Then we have two other terminals, that is 7 and 4. So at 7 we are connecting positive DC supply. We are writing it as VCC. VCC means the DC supply is connected at the collector terminal of BJT. Basically, in op-amp, we are having different kind of differential amplifier. We are having direct coupled BJTs inside of this IC. So we have to provide supply to those BJTs. So this is the plus VCC, and here we are having minus VCC. This is minus VCC, and we can write it as this is V2, this one is V1, and the difference of these two voltages is V1 minus V2, that is going to be amplified. So this is known as the VID, that is the difference of input signals. So we are writing it as VID. This is the difference of input signals. This is the difference of input signals. So basically this particular voltage is going to be amplified. And we have two other terminals also that are mentioned as 1 and 5. These two terminals are known as offset null. These are known as offset null. So this is the symbol of operational amplifier. This is the simple symbol of operational amplifier, in which we are having different pins also. 8 number pin that we had discussed earlier is not connected. We don't have any kind of use of that pin. So this is the symbol, and after that we will proceed. And what is the working principle of operational amplifier? So we have seen that it will always amplify the difference of input signals. It will always amplify the difference of input signals. So here we can write the gain. We can write the gain of operational amplifier is, that is denoted by A, is V output divided by V input. So in op-amp, we are having difference of input signals as input voltage. So here this V input will be the difference of input signals, that is VID, that can be written as V1 minus V2. This can be written as V1 minus V2. So here we have output voltage as A times V1 minus V2. A times V1 minus V2. So this is the open loop gain. This can be called as open loop gain. Open loop gain of op-amp. Open loop gain of op-amp. Why we are calling it as open loop? Because we don't have any kind of connection between output and input terminals. As we have seen, 6 number pin is used for output, and 2nd and 3rd number pin is used for input. So there is no direct connection between input and output. So whatever gain we will find here, that is A naught, that is known as the open loop gain of operational amplifier. And we remember the value of this gain is very high. The value of this gain is very high, and this is not a controlled output. This is not a controlled gain, because as we increase these voltages, as we increase V1 or V2, means if the difference of these two voltages are increasing, then this output will go to the saturation region. This output will become a fixed value. So we will discuss about it. So this A naught is the open loop gain. Similarly, if your output is connected with the input terminals, then we have closed loop gain also, ACL. We can call it as closed loop gain. And we remember, if we are having feedback, means output is going to connect it with the inverting terminal of operational amplifier, then we will get a controlled gain. This is a kind of controlled gain. This is having a controlled value. So this is the working principle. Working principle is similarly we can see here this is a kind of linear equation. We can write it as y is equal to mx. Y is equal to mx. So this is a linear equation. So we can perform different linear application by using operational amplifier, but it cannot be performed through open loop gain. Open loop configuration, we cannot perform linear applications because as we increase these two voltages, as we increase V1 or V2, this output will go to the saturation. So this is the working principle of operational amplifiers. So now we are going to discuss about the characteristics of an ideal operational amplifier. What should be the characteristics of an ideal operational amplifier? So here we know that for any kind of amplifier, the input impedance or input resistance must be infinite, and output resistance or impedance should be zero. So here we are having first we are writing as gain. This is the gain that we have seen here. It is written as gain, that is V output divided by VID, and this should be infinite. This should be ideally infinite. Even if we don't provide any kind of input, there should be a desired output. This is the condition. This is the ideal condition that we want. So for that, this must be infinite. This is the ideal condition. This should be infinite. Second is input impedance. That is also known as input resistance. Input impedance or input resistance for any amplifier, we know that this should be infinite. This should be infinite. What will happen if this is infinite? Suppose this is the operational amplifier, this is minus plus, this is the inverting terminal, this is non-inverting terminal, this is V1, we can call it as V2, so V1 minus, V2 is the difference of these two signals, and input resistance is always be here. This is the input resistance, and if this resistance is infinite, what will happen? These two terminals will become isolated. There will be no interference. There will be no interference between inverting terminal and non-inverting terminal. So we are assuming this condition for ideal operational amplifier, the input resistance or impedance should be infinite. Then we have output resistance, or we can write output impedance. This should be zero. Ideally, this should be zero. Whenever we have any kind of output, we don't want to lose any value. So this is zero. If this value is zero, then whatever output we are getting, that will be reflected at the load of the operational amplifier. Fourth is we have bandwidth. This is the bandwidth. Bandwidth basically decides that what kind of frequency that is going to be amplified through operational amplifier. So we know that in ideal case, any kind of signal, any kind of analog signal of any frequency, either DC signal or AC signal, 0 hertz to infinite hertz. This is the desired situation. So if it is happening, then bandwidth must be infinite. Bandwidth should be infinite. That is the ideal condition. Bandwidth should be infinite. Then next we have infinite common mode rejection ratio. We have infinite common mode rejection ratio. What is the meaning of this term? This is written as CMRR. In short form, it is written as CMRR, that is common mode rejection ratio. Common mode rejection ratio. So basically this term implies the noise rejection. This term implies the noise rejection by operational amplifier. That how much noise can be rejected through operational amplifier, this will be decided by common mode rejection ratio, and ideally this must be infinite. If the value of CMRR is infinite, that means there is no noise present in the circuit of operational amplifier. So this we can write as noise rejection. This represents the noise rejection capability of noise rejection capacity. Noise rejection capability of any operational amplifier. So this is CMRR. Then again we have PSRR. This is known as power supply rejection ratio. We can write it as power supply rejection ratio. This is a very important term to understand because we are providing external DC supply. We have seen in symbol as well as in pin diagram that we are giving two external DC supply. Like here, we can make it like this, minus plus. This is V2. This is non-inverting terminal, that is V1. This one is output. Here we have two external DC supply, that is plus VCC and minus VCC. If there is any change in these supplies, then output should not be changed. Output should not be vary. If there is any increase in the DC supply value, the output should be fixed. This is represented by PSRR, that is known as power supply rejection ratio. If we are increasing the value of DC supply, then output should not be changed. This must be a fixed value. So this is the PSRR, and ideally the value must be infinite. Ideally, the value should be infinite. So this is the PSRR. Then we have next is zero offset voltage. This is also very important term to understand. Zero offset voltage. What will happen if the value of V1 become V2? If the value of V1 become V2 means if the both signals are equal. If both signals are equal, then what will happen? The output should be zero. The output should be zero, but it is not happening because of zero offset voltage. Then we have slew rate. This is a very important term to understand. Slew rate is basically if we are doing any kind of change in input signal, then it must be reflected at the output also. If we are changing our input signal, then it should be instantaneously reflected at the output. In mathematical form, slew rate is defined as the maximum change in output voltage with respect to time. As we are changing the input, if instantaneously the output is changing, that means slew rate value is infinite, and unit is represented as volt per microsecond. So for ideal case, this value also be infinite. So these are the ideal properties of operational amplifier. So we have seen that gain should be infinite, input impedance must be infinite, output resistance or impedance should be zero, bandwidth must be infinite, CMRR is infinite, PSRR is infinite, zero offset voltage should be there, and slew rate must be infinite. So this is the ideal operational amplifier properties. So now we are moving further. We have equivalent circuit of an operational amplifier. This is also a very important topic to understand, that how can we represent operational amplifier as an equivalent circuit. So here we have the symbol of op amp that we are making here. This is the symbol of op amp. This is inverting terminal. This one is non-inverting terminal. Why we are writing it as minus and plus, that we will discuss later. And then this is the output terminal, V output. This is inverting terminal. This one is non-inverting terminal. We can write it as V1. This is V2. This is at second number pin. This is third number pin. Output is available at 6 number pin, and we have two DC supply here. This one is plus VCC, this is minus VCC. So this is the symbol. Now it will amplify. We know that what will be the VID? VID is the difference of V1 minus V2. We can write it as V1 minus V2. This difference is going to be amplified. So input resistance is here. This is the input resistance. This is input resistance. So we want to make the equivalent circuit of this operational amplifier. So here we know that gain is output divided by input, and here we are having VID because operational amplifier always amplifies the difference of input signals. So we are writing VID. So this will implies V output as A into VID. A into VID. Output can be written as A into VID. So we may have Thevenin equivalent. We may have the Thevenin equivalent. Here we are having a dependent voltage source. We are having a dependent voltage source in which value is depending on the input. Value is depending on the input voltage that we can write at VID. And here we have Thevenin resistance as R output. This is the R output that is at Thevenin resistance. We must be aware of Thevenin's theorem. This is the RTH value and this will be the VTH value. So this becomes the equivalent circuit of operational amplifier, in which practically we have some value as R output, and here this is also having some kind of value, but in ideal case this R input is infinite and this R output is 0. So this is the equivalent circuit of operational amplifier. So we are utilizing the Thevenin's equivalent. We are utilizing the Thevenin's equivalent means if we have any kind of circuit, linear circuit that can be represented through one voltage source that is known as Thevenin voltage in series with a resistance that is Thevenin resistance, and here we are having the load. Here we are having a load resistance that is RL. So how we can calculate this RTH? RTH can be calculated by shorting all voltage sources. Sorting all voltage sources means voltage should be 0. Voltage should be 0, and removing all current sources. Removing all current sources means current source जितने लगे हैं उनको हटा देंगे, voltage source जितने लगे हैं उन्हें short कर देंगे. I should be 0. So by utilizing these two conditions, we are calculating RTH, and this RTH is always output resistance in operational amplifier that we have seen in equivalent circuit of op-amp. So now we proceed further. This is the ideal voltage transfer curve that is very important to understand. This will provide us the clue why we are not utilizing open loop configuration of operational amplifier for linear application. We cannot perform linear applications like adder, subtraction, integrator, differentiation, etc. by using open loop configuration. So this is a very important topic to understand, that is ideal voltage transfer curve. So here we must know about three things. If any graph is drawn between two scale, suppose this is X, this one is Y. This is X, this one is Y. If X and Y both are belonging to the input side. These two parameters are of input side. So whatever characteristic we will make by considering x and y, that is always be known as input characteristics. If these two parameters, these two variables are of input side, so then we will make the characteristic that is always be called as input characteristics of that particular system. And if x and y, these two parameters are belonging to output side of the system, this is belonging to output side of the system, then if we are making any kind of characteristics by using these two parameters, by taking these two parameters in scale, so this is known as output characteristics. This will be known as output characteristics. And if one variable is of input side and other variable is of output side, then characteristic made will be known as the transfer characteristic. Characteristics made will be known as transfer characteristic. This is very important to understand that we are going to make transfer curve. Here in operational amplifier, we are going to make transfer curve, means this curve is drawn between V output and VI, that is VID. So this is V output is the parameter of output side and this VID is the parameter of input side. So we are drawing a curve between one parameter belonging to input side and another parameter belonging to output side. So such curve is known as the transfer curve. So now we are making a curve here. This is ideal voltage transfer curve. So here we are having two scales. One is, let's say, this is VID. That can be written as V1 minus V2. This is VID. Here we are having minus VID. This is the output. Here we also have minus of output. So we are aware that there is a linear relationship between gain and output. How we can write it as V output is always A times VID. This is a linear equation that can be written as Y is equal to mx. So as we increase the value of V1 or the value of V2, it will increase linearly. So what will happen as we increase the value of V1, this will increase linearly like this. And similarly, if we increase the value of V2, so this will increase linearly like this. But after a certain voltage, this will be saturated. Output will become saturated. This value is positive V saturation. After a certain voltage, output will become fixed value, that is plus V saturation. And similarly, in negative quadrant, this will become minus of V saturation. This is when V1 is greater than V2, and this is happening when V1 is less than of V2. So this is the ideal transfer curve. So how we can explain? We can explain it like when we have a small change in VID, then there is a variation, that is linear variation. But after a certain value, after this value, the output will become saturated. So be remember, open loop configuration always provide us the saturated value. As we increase the input voltages, output will become saturation, output will become fixed value. Output will provide us a fixed value. That's why operational amplifier in open loop configuration can never be used as for linear applications, as for performing the linear application. So we can write here open loop op amp cannot perform linear operations. This is very important to understand, that operational amplifier in open loop configuration cannot perform linear application. So we have to do feedback. We have to connect output terminal to any of the input terminal. Now we will decide that which configuration will be best suitable to perform linear application, because if we connect output to inverting terminal, then it will be a negative kind of feedback. It will be a negative feedback. If we are converting output voltage to non-inverting terminal, then it will be known as the positive feedback. So which closed loop configuration will be utilized for linear application, that we will decide. But here in ideal voltage transfer curve, we have seen that output is going to be saturated after a certain voltage. So operational amplifier in open loop configuration cannot perform linear application. It can be used. You can write here, it can be used as comparator. So what is the basic application of open loop configuration of operational amplifier? This is the comparator. So now we need to move further. We have operational amplifier practical parameters that we have studied earlier. There are so many parameters for which we have seen the ideal values. Now we are going to discuss about the practical. Op amp parameters. So here we have first is input offset voltage. This is very important to understand. Input offset voltage. So here we can write if inverting terminal, you can write here, if inverting terminal and non-inverting terminal are grounded. Grounded means V1 is also become 0, V2 is also become 0. So what will happen in this particular situation? If V1 is 0 and V2 is 0, in this situation the output must be 0. We can write here, then output should be 0. But it is not happening practically. Practically, we will get some kind of output. Since we are grounding both of the terminals, V1 and V2, still we are getting some kind of output. Why it is so? Because of imbalance in the circuitry. Imbalance in circuit. What does it mean? What is the meaning of imbalance? Basically, we are utilizing different bipolar junction transistors for making operational amplifier. and the values of alpha, beta, gamma means current gains values must be equal enough. Then only we will get the ideal values. Since the values of these current gains are different, so this is known as the imbalance in the circuitry, and because of this imbalance we are getting some output because of DC supply applied at terminal 7 and 4. So we are not getting zero output. So this is known as the input offset voltage. We are having some value because of DC voltage connected at 7 number pin and 4 number pin. So the difference of these two values, VDC1 minus VDC2, is known as the input offset voltage. Is known as input offset voltage. This is called as the input offset voltage. What is VDC1? This is positive supply that is connected in op-amp. This one is, we can say, negative supply. So this is known as the input offset voltage. Even we are grounding both of the terminal, still we are getting some kind of output because of imbalance in the circuitry. That is called as the input offset voltage. Similarly, we have input offset current also. We also have input offset current, like there should be equal currents in both of the circuits. This is V2, that is inverting terminal. This one is V1, that is non-inverting terminal. This is the base current flowing in inverting terminal, that is IB2. Here we have IB1. These two current must be equal. IB1 should be equal to IB2. This should be the condition. But because of imbalance in the circuitry, we have some difference between these two currents. We have some difference between these two currents, and the difference of these two currents is known as input offset current. We can write here, this is IB1 minus IB2. This is input offset current. This is known as the input offset current. What is IB1? IB1 is basically, this is the current in non-inverting terminal. This is the current in non-inverting terminal. This is the current flowing in non-inverting terminal, and this is the current flowing in inverting terminal. This is the current flowing in inverting terminal. Maybe this is not visible, so I'm writing again here. This is current in non-inverting terminal. So this is the input offset current, means these two current must be equal. This should be the condition, but because of imbalance in the circuitry, these two currents are not equal. So whatever we have, the difference is known as input offset current. After that, we have bias current. Bias current is basically the average of input offset current. We can write it as IB is equal to, basically this is the average of, IB1 and IB2. We can write here, this is the average of IB1 and IB2. So this is known as bias current. Bias current is the average of IB1 and IB2. So this is known as the bias current. So again, after that, we have one more parameter that is known as slew rate. So earlier, as we have seen, the ideal value of slew rate is infinite. That represents if we are doing any kind of change in input signal. If we are changing our input signal, that must be reflected at the output. So slew rate is basically, we can write it as slew rate. Slew rate can be written as slew rate can be written as the maximum change in output with respect to time. With respect to time. Ideally, the value of slew rate is infinite, so we can write it as d by dt of V output and the maximum change. So this is the definition, this is the mathematical representation of slew rate. So we can write it as Vp into W. So unit can be written as volt per microsecond. So this is Vp into 2 pi f. This can be written as Vp into 2 pi f, where what is Vp? Vp is the maximum value of output voltage. Maximum value of output voltage. And what is the frequency? Frequency is f is the input frequency. F is the input frequency. So for ideal case, slew rate has to be infinite, that we have seen earlier. This is the slew rate. After that, we have this parameter that is very important to understand. This is known as common mode rejection ratio. So this is a kind of noise rejection capability of operational amplifier. In mathematical form, we can write CMRR. We know that. What is this? This is common mode rejection ratio that represents the noise rejection capability. In mathematical form, we can write it is the ratio of differential gain versus common mode gain. This is the ratio of differential gain versus common mode gain. Like we have this op-amp, this is the output, minus plus, this is V2, this is inverting terminal, that is V1, and we are amplifying the difference of these two signals, that is VID. VID is basically V1 minus V2, and we have two DC supply here, plus VCC and minus VCC. So here we can write AD as V output divided by VID. This is the differential gain. Here we are considering the difference of the voltages. What we'll do, if we common these two terminals, that is V2 and this is V1, this is V output. And if we are providing a common voltage to both of the inputs, let's say this is VCM, that is the common mode voltage, given to both of these inverting and non-inverting terminals. So here we can get common mode gain as V output divided by VCM. V output divided by VCM. So the difference of these two gains, is known as CMRR, that is called as the common mode rejection ratio. So now we will proceed again. So this is all about the open loop configuration. This is all about the open loop configuration of operational amplifier. Basically, till now we have discussed the pin diagram of the open loop, symbol of the open loop, and different kind of properties of operational amplifier that we are going to that we have already discussed. Now, what kind of configuration that we can make through operational amplifier, that we are going to discuss. This depends on which particular terminal we are applying the input. At which terminal we are applying the input, that will decide the configuration of open loop circuitry. So this is the open loop configuration. So here we have three configuration. One is known as inverting operational amplifier. One is known as non-inverting configuration of op-amp, and another one is differential operational amplifier. So we will discuss these three configuration of operational amplifier. So we are taking a break of 5 minutes, and after that we will meet again. Thank you. Hello, welcome back again. So now we are doing so this is the open loop configuration that we are going to discuss. So here we have three configuration. One is one is inverting op amp. We can write here as inverting op amp. Another one is non-inverting op amp. And third one is differential op amp. So these are the three configuration of open loop op amp. So here we must know that in inverting operational amplifier, the input is connected only at inverting terminal of op amp. Similarly, non-inverting terminal will be grounded in case of inverting op amp. In non-inverting op amp, we are connecting our input signal only at non-inverting terminal, and inverting terminal will be grounded. And if the inputs are connected at both of the terminal, inverting as well as non-inverting, then this is known as the differential operational amplifier. So we are going to analyze these three configurations. So first is inverting op amp. So here we have this op amp that is inverting terminal. This is V2. This one is V1. This one is V output. So we want to make this inverting op amp. So what we will do, we will connect it voltage at inverting terminal. Here we have V input 2. This is the voltage connected at inverting terminal, and non-inverting terminal is grounded. This non-inverting terminal is grounded. So it will amplify the difference of these two signals. So the difference is V1 minus V2. Here we have V1 minus V2. This difference is going to be amplified. So what will be the output? The output will be simply A times V into ID. This is A times V into ID. We know that gain is always the difference of output voltage to input voltage. In operational amplifier, we have difference of the input terminal. So this is VID. So we can write here at A into VID is V1 minus V2. Here V1 is grounded. So we can write V1 as 0. And what is V2? V2 is connected with an input terminal, that input voltage, that is V into. So we can replace these values. So output will become A into 0 minus V into. That we can write here minus of A into V into. This is the output. So what we have seen, there is a minus sign. There is a minus sign when we have connected input voltage at inverting terminal. So we are getting output as minus of A times of V input 2. So what this negative sign represent? Basically, this negative represents that there is a phase shift. There is a phase shift of 180 degree between this output and this input. So we can make this through structure. Here we have input as this. This is V input. What will be the output? Output will be like this. Output will be 180 degree. 180 degree phase shift with input. So this is the output. This is the output. There is a phase shift of 180 degree. There is a phase shift of 180 degree in case of inverting amplifier. in case of inverting operational amplifier. So we have connected input at inverting terminal only, and non-inverting terminal is grounded. So similarly, we can discuss non-inverting operational amplifier also. So in non-inverting operational amplifier, we will connect voltage only at non-inverting terminal. So this is the op-amp. This is the op-amp minus plus inverting terminal, that is V1. This is non-inverting terminal, that is V2. Now this is inverting terminal V2. This is non-inverting terminal V1. And now we are grounding this terminal. This is the inverting terminal that is now grounded. And we have connected a voltage source here. Let's say this is V in 1. So we have connected a voltage source at non-inverting terminal. So this is going to be amplified. That is the difference of these two voltages, V1 minus V2. So what will be the output? We can see the output is basically, gain is A is equal to V output divided by VID, that we can write at V output divided by V1 minus V2. So here in non-inverting op-amp, V1 is equal to V input 1. This is the voltage source we had applied at non-inverting terminal. And V2 is 0. Inverting terminal is grounded. So we can write here V output is equal to A times V1 minus V2. So this will be simply plus A times V1 is V input 1 minus 0. Minus 0 we have written as V output as plus of A times V input 1. So what this plus sign represent? This represent that there is no phase shift. There is no phase shift between input and output. Output is A times larger than V input 1, means signal is amplifying, but these two signals are in phase. So we can write here, suppose this is the input. So we will get output like this. The signal is amplified but in phase. This is the output, and there is a phase shift of 0 degree between this input and output. So in inverting op-amp, we are getting a minus sign. Minus sign represents that there is a phase shift between input and output of 180 degree. While in non-inverting operational amplifier, we have this plus sign. That means there is a phase shift of 0 degree between input and output. In differential amplifier, we will connect voltage sources at inverting as well as non-inverting, and whichever voltage is higher, according to that we will get the output. So this is all about operational amplifier in open loop configuration. Now we have this closed loop configuration. That is very important to understand, because operational amplifier in open loop configuration cannot be used for linear application. We cannot design adder, subtractor, integrator or differentiator by using open loop configuration. That we have seen in ideal voltage transfer curve, that as we increase the input voltage difference, the difference of input signals, the output is going to be saturated. So we need to do a feedback. We need to have a feedback. Here we have connected this output with a terminal. Here we have connected this output with inverting terminal. So this is a kind of negative feedback, and we need to do a negative feedback for linear application, because if we are getting some kind of output to the input, then it should be in out of phase, so that it can reduce the input signals. If input signal is getting reduced, then we will not get the saturated output. So that's why we are utilizing the negative feedback. We are utilizing the negative feedback means output will be connected with inverting terminal. This is the inverting terminal that is at 2 number pin. This is 3 number pin. This is 6 number pin. So we will connect output to the inverting terminal for making circuits of linear applications. So this is the closed loop configuration. So we will move forward. So here we have closed loop configuration means some part of output here we can write some part of V output is feedback to input terminal. Feedback to input terminal. This is the closed loop configuration. If output is connected with inverting terminal, if output is connected with inverting terminal, if output is connected with inverting terminal, then this is negative feedback. Then this will be the negative feedback. If we have connected output to inverting terminal, then this will be the negative feedback. Similarly, we can also write if output is connected with non-inverting terminal, then this is known as positive feedback. Then this is known as positive feedback. So basically we have two configuration of closed loop. One is negative feedback configuration, one is positive feedback configuration, and for linear application we will utilize the negative feedback configuration, in which we are going to connect output to inverting terminal via a resistance that is known as RF. This is the feedback resistance. So output is feedback to the input, and that input will be the inverting terminal. So this is the closed loop configuration. So now we are going to discuss non-inverting operational amplifier, and this is very important to understand that how can we design this non-inverting operational amplifier through negative feedback. Means it is also a kind of closed loop configuration in which we are utilizing the negative feedback to get an output with the help of this feedback resistance. So we are getting this circuit. So non-inverting amplifier, we want to design this non-inverting amplifier. So here we have the symbol of op-amp. This is op-amp, that is minus, this is plus, this is the inverting terminal, this one is non-inverting terminal. So we have this voltage V1, this one is V2. Here we are having output. And this is V1 minus V2, that is the difference of the signal, VID, that is V1 minus V2, and we are connecting this inverting terminal to output. Basically output is feedback to the inverting terminal through a resistance RF. This is RF. And since this is the non-inverting amplifier, so we have to connect input voltage at non-inverting terminal. So this is a voltage that we are connecting here, that is plus and minus. This one is V input, and here we have a resistance, that is R. So here what we have connected input signal at non-inverting terminal. This is the non-inverting terminal where we have connected this input signal, and inverting terminal is grounded. Inverting terminal is grounded, but the output is feedback to the inverting terminal. Output is feedback to the inverting terminal. So this is the non-inverting operational amplifier, and we want to do the analysis of this circuit. So for doing analysis, we must be aware about the virtual ground concept. We have to understand the virtual ground concept. So remember, we are discussing the virtual ground concept. Just wait a minute. I'm just coming back. So we are going to discuss about the virtual ground concept. Then we will do the analysis of inverting amplifier and non-inverting amplifier. So here we are going to design inverting operational amplifier as we have designed non-inverting amplifier, in which we have connected input voltage at non-inverting terminal and inverting terminal was grounded. Similarly, we can design this inverting operational amplifier through closed loop configuration, in which we are connecting input voltage at inverting terminal. So this is minus, this one is plus. This is the output voltage, that is V output, 6 number pin. This is second number pin, that is inverting terminal. This one is third number pin, that is non-inverting terminal. We have voltage at V1. This is V2. So the difference will be V1 minus V2 that we are going to amplify. We have connected a resistance. Let's say this is R1, and we are going to connect a voltage, that is plus minus. This voltage is V input. As we have seen earlier, when we have designed non-inverting amplifier, in which we have connected voltage here at inverting terminal. So this is V in connected at inverting terminal, and this particular non-inverting will be grounded. Why this non-inverting terminal is grounded? Because we are making inverting operational amplifier. So whatever input we are applying, that should be at inverting terminal, and we have a feedback. Since this is the closed loop configuration, so we have a feedback. Output is connected with inverting terminal with a resistance RF, So this is VID, and this is the inverting operational amplifier. This is the inverting amplifier. This is the circuit of inverting amplifier. And now we want to do the analysis of this circuit. So first we need to understand virtual ground concept. This is very important to understand that what do you mean by virtual ground concept. This is called as virtual ground concept. Virtual ground concept. virtual ground concept. For doing analysis of any kind of amplifier that is in closed loop configuration, we must be aware of virtual ground concept. This is very important to understand. After that, we will do the analysis of this circuit, means we will calculate the output voltage of inverting operational amplifier. Then we will calculate the output for non-inverting amplifier. So what do you mean by virtual ground concept? So basically, we know that here we can write, we know that gain is output divided by input. Output divided by input. So in op-amp, we have input as difference of the voltages, that is VID, that we can write here at V1 minus V2. So this can be written as A is equal to V output divided by V1 minus V2. If gain is infinite, so what will happen? We can write V output is equal to A times V1 minus V2. V output is equal to A times V1 minus V2. And here we can write it as, V1 minus V2 is equal to V output divided by A. So if this gain is infinite, if we are considering the gain is infinite, what will happen? This will become 0. That means V1 is equal to V2. V1 is equal to V2. This is the condition of, this is virtual ground concept. This is the condition of virtual ground concept that we can write here. What does it mean? Whatever is the voltage at non-inverting terminal, whatever is the voltage at non-inverting terminal, that is automatically considered or reflected at inverting terminal if gain is infinite. If we are considering gain as infinite, then whatever voltage present at non-inverting terminal, that is automatically going to reflect at inverting terminal of operational amplifier. So we are going to use this virtual ground condition for doing the analysis of different amplifiers, different linear applications. So here now we can do the analysis of inverting amplifier. So this is the circuit. So we have the circuit. This is the circuit, that is minus, plus. This is V output. This is very important to understand because similar kind of analysis we will do for all kind of circuits. And then we have this inverting terminal as V2. This is non-inverting terminal. This is the feedback resistance, that is RF. We have connected here at a resistance, that is R1. And voltage is also connected at this terminal, that is B input plus minus. And non-inverting terminal is directly grounded. Non-inverting terminal is directly grounded. and the voltage between these two terminals is V1 minus V2. So this is the inverting amplifier circuit, and now we are going to analyze this circuit. We want to find out the output voltage of this circuit. And here we have two DC supply also, that is plus VCC, this is minus VCC. So first we will consider the node A. Let's say this point is A. This node is A. So we can write here at node A. In this particular node, we can see that there are, this is a junction. Here we have a current. Let's say this is I2. This current is I2. At junction A, this current is I2. We have a current here. Let's say small I. This is the small I current. And current flowing through this RF resistance is IF. So at this junction, we can apply Kirchhoff current law. So what will happen? We can write I2 is equal to small I plus IF. I2 is equal to I plus IF. Here this is I2 is equal to I plus IF. And we remember we have considered the infinite input resistance. Here we have input resistance that is infinite. So what will be the value of this current? This current value is 0. This I will be 0. Here also I will be 0. So this I current is going to be 0. Now we want to write the value of I2. What will be the value of this current I2? So this can be written as V input. This is the voltage V input minus voltage at this particular junction A. So at this junction voltage is V2. So V input minus V2 divided by R1. This will be the value of I2. The voltage difference is V input minus V2 divided by the resistance connected here R1. So this is the value of I2. Similarly, we can write the value of I1. How can we write it? This is voltage here is V2. V2 minus V output divided by RF. So we can write it as V2 minus V output divided by RF. So this is the equation number 1. So similarly, we have applied KCL here, and this is the I2 current. Small I current becomes 0, and this is the feedback current IF. And then we have written the values of these currents. This is the V input minus V2 by R1. This is V2 minus V output by RF. So here we can see what is the value of V1. Here V1 is equal to 0. Since this terminal is grounded, so what will be the value of V1? V1 is 0. Hence by virtual ground concept, we can write V1 is equal to V2, that is also be 0. That is also be considered as 0. So now we are putting this value in equation number 1. So we are moving again. So we will have here, we are having V input minus V2 divided by R1. This is equal to V2 minus V output divided by RF. So since V1 is 0, hence by virtual ground concept, V2 is also be 0. So we are putting this value here. So what will be the value? V input minus 0 divided by R1 is equal to 0 minus V output divided by RF. So V output will be minus of RF divided by R1 into V input. V output is minus of RF divided by R1 into V input, and this minus sign represents that the input was connected at inverting terminal. So there is a phase shift of 180 degree between input and output, between this input and output. This is the phase shift of 180 degree. Since we have connected our input signal at inverting terminal, that's why we are getting this minus sign. So this is the analysis of inverting op amp. So here we have input as this. This is the V input, and output is like this. This is the output, that is minus of RF divided by R1 into V input, and there is a phase shift of 180 degree between input and output. So this is all about inverting amplifier in closed loop configuration. Similarly, we can do the analysis of non-inverting amplifier. We will do the analysis of non-inverting amplifier. See here. So we are making the circuit of non-inverting. This is minus, this one is plus. This is output. That is, we are getting at 6 number pin. And we have inverting terminal. This is the non-inverting terminal. A feedback resistance is connected here between inverting terminal and output. This is the feedback resistance. And since this is the non-inverting amplifier, so we will connect our voltage here. This is the voltage that we are connecting at non-inverting terminal. This is V input. And here we have a resistance R1 that is directly grounded. So here we have connected input at non-inverting terminal. That's why this is the non-inverting amplifier. And this is the point that is called as A. This is the node A where we will apply the Kirchhoff current law. So here we can write at node A, let's say this current is I2. Again, we are writing this current as I2. This is small I and this is IF. So what will happen? I2 will be is equal to small I plus IF. Small I plus IF, and this current is 0. How can we write I2? I2 is simply 0. 0 minus this voltage is V2. So we can write 0 minus V2 divided by R1 is equal to IF. IF is V2 minus V output divided by RF. I2 is flowing between this A point and output. So A point voltage is V2. So V2 minus V output divided by RF. So this is the equation number 1. And here V1 is equal to V input. So by virtual ground concept, we can write V1 is equal to V2 is equal to V1. So we are going to put this V2 value in equation number 1. What will be the value? 0 minus V2 is V input divided by R1 is equal to V input minus V output divided by RF. So we can simplify this as minus V input into R1 is equal to V input into R1 minus V output, this is RF, minus V output into R1. So what will happen? We are going to combine output and input separately. So this will become V output into R1 is equal to V input, that is R1 plus RF. So here we can write V output is equal to 1 plus RF upon R1, 1 plus RF upon R1 into V input, RF upon R1 into V input. So this is that we are getting that output is 1 plus RF upon R1 into V input. That means there is no phase shift between input and output. So this is all about non-inverting amplifier. So similarly, we can make the unity gain amplifier also. Since for, we can write here for non-inverting amplifier, we are having output as 1 plus RF upon R1 into V input. RF upon R1 into V input. Now unity gain amplifier means the gain should be 1. Gain should be 1 means output must be is equal to input. So that implies output should be equal to input. So how can we make this? We can make it by considering RF as 0 and R1 as infinite. RF as 0 and R1 as infinite. So this can be the circuit. We have seen non-inverting amplifier. This is minus, this one is plus. So RF is 0 means this becomes 0. This is the output. So this RF becomes 0. Here RF is 0. And this R1 is become infinite. And we have connected input here. So this becomes the circuit of unity gain amplifier in which RF is 0 and R1 is infinite. So there are many other topics that are left. After that, we are going to discuss about, we want to discuss about summing amplifier, subtractor, also integrator and differentiator. So all of these circuits can be analyzed by using virtual ground concept, and we may have the relevant output of all these linear operations. So this is all about linear integrated circuit basic operations. And today we have discussed operational amplifier. This is an important topic of linear integrated circuit. And in coming lectures, we will discuss other topics also related to this subject. Thank you all. Thank you for your patience. And if you have any query related to the lecture that we have discussed till now, please let me know. If anyone is having any kind of query, please let me know. Am I audible to all of you? Are you getting my voice? अगर कोई क्वेरी है तो हम डिस्कस कर सकते हैं. So thank you everyone for joining us, and we will meet again with some other topics related to this subject, linear integrated circuit. Thank you all.
थैंक यू सुनील सर. और इसी के साथ हमारा ये सजीव व्याख्यान का सेशन समाप्त होता है। आप सभी के द्वारा कोई क्वेरी नहीं पूछी गई। इसका दो ही मतलब है,
Can
या
you
तो आपको
explain
सब
it?
समझ में आ गया या फिर कुछ समझ में नहीं आया। तो प्लीज आस्क इफ यू हैव एनी क्वेरी। अभी भी सुनील सर हमारे साथ हैं, और अगर यहाँ से आपको वॉइस ऑडिबल है, इफ आई एम ऑडिबल टू ऑल ऑफ यू, इफ यू हैव एनी क्वेरी
Can
और
you
यस यस प्लीज टेल मी।
can you explain slew rate?
लव तिवारी जी की आवाज आ रही है।
लव तिवारी, बेसिकली स्लीव रेट इज लाइक, अगर हमने इनपुट में कोई भी चेंज किया तो ऑब्वियसली उसका उस चेंज का इफेक्ट आउटपुट में दिखना चाहिए, और वो कितनी देर में दिखता है। हम ये चाहते हैं कि अगर इनपुट में हमने जो भी चेंज किया, दैट शुड बी रिफ्लेक्टेड एट द आउटपुट इंस्टेंटली, उसी टाइम पर आउटपुट में दिख जाना चाहिए। दिस बेसिकली रिप्रेजेंट स्लीव रेट कि व्हाट इज द मैक्सिमम चेंज इन द आउटपुट विद रिस्पेक्ट टू टाइम।
Thank you, sir. One query is more. Input offset voltage, can you explain me?
Input offset voltage, yeah. Suppose the voltage connected at non-inverting and inverting terminal both are grounded, दोनों ग्राउंडेड है। इसका मतलब क्या हो गया कि इन्वर्टिंग का टर्मिनल का जो वोल्टेज है V2 वो भी जीरो हो गया, नॉन इन्वर्टिंग टर्मिनल का वोल्टेज भी जीरो हो गया।
जी सर।
तो जब दोनों वोल्टेजेस जीरो हैं तो हमारे पास जो आउटपुट आना चाहिए वो भी जीरो आना चाहिए। यस और नो?
जी सर। Yes, sir.
यस। बट व्हाट इज हैपनिंग, हमने बीच में डीसी सप्लाई लगाई हुई है जो ट्रांजिस्टर्स को ऑन करने के लिए यूज होती हैं। तो उन डीसी सप्लाई की वजह से इम्बैलेंस इन सर्किटरी में इम्बैलेंस होने की वजह से हमें कुछ आउटपुट मिल जाता है, और वो जो आउटपुट मिलता है उसको हम कहते हैं इनपुट ऑफसेट वोल्टेज। उसको हमें जीरो करना पड़ता है, जिसके लिए हम 1 नंबर और 5 नंबर की जो पिन बताए थे पिन डायग्राम
जी
में,
सर।
उन
जी सर।
पर्टिकुलर पिन्स पर जब हम वोल्टेज लगाते हैं तो इस आउटपुट को जीरो कर सकते हैं।
Thank you, sir.
Any other query that I can answer?
No, sir.
Okay, thank you all. Thank you so much.
Someone else? I'll wait for 1 more minute and then I'll conclude this lecture.
There are many other
सर
topics.
वर्चुअल ग्राउंड को
हाँ,
वर्चुअल ग्राउंड को एक बार समझा दीजिए।
वर्चुअल ग्राउंड कॉन्सेप्ट बेसिकली, अगर हमने किसी ऑपरेशनल एम्पलीफायर के गेन को इनफाइनाइट कंसीडर किया, उस सिचुएशन में जो भी नॉन इन्वर्टिंग टर्मिनल पर वोल्टेज होता है दैट इज गोइंग टू बी कंसीडर्ड एज इन्वर्टिंग टर्मिनल वोल्टेज। हमने एक्सप्लेन किया था व्हेन ए इज इक्वल टू इनफाइनाइट, जब गेन आपका इनफाइनाइट हो जाएगा, so V1 become V2, V1 is equal to V2. So whenever we do the analysis of different circuits of operational amplifier, we will consider this virtual ground concept to get the maximum output. And you can analyze all kind of circuitry. इसके बाद भी अभी बहुत सारे और सर्किट्स हैं, लाइक आपके एडर हैं, समिंग एम्पलीफायर हैं, सब्ट्रैक्टर है, इसके अलावा इंटीग्रेटर, डिफरेंशिएटर। चूंकि टाइम कम पड़ गया तो हम लोग ये डिस्कस नहीं कर सकते, बट वी हैव लॉट ऑफ एप्लीकेशन जो लीनियर एप्लीकेशंस हैं। वी विल डू एनालिसिस ऑफ ऑल दीज सर्किट्स बाय कंसीडरिंग वर्चुअल ग्राउंड कॉन्सेप्ट, जिसमें आपको गेन इनफाइनाइट मानेंगे तो जो भी वोल्टेज नॉन इन्वर्टिंग टर्मिनल पर है वो ऑटोमेटिकली इन्वर्टिंग टर्मिनल पर कंसीडर होता है।
इट इज काइंड ऑफ सॉर्टेड, प्रैक्टिकल पर्पसेस के लिए उसको सॉर्ट करके ये मान चलते हैं कि सॉर्टेड है, और सारे न्यूमेरिकल्स वैल्यूज भी हम लोग उससे अचीव करते हैं। बिल्कुल संकोच मत करिए, अगर किसी को पूछना है तो पूछ लीजिए। पूछने का मतलब ये नहीं कि आपको नहीं आता है, पूछने का मतलब ये होता है कि आप इंप्रूव करना चाहते हैं।
इफ यू आर आस्किंग मीन्स आपने सुना है।
Okay,
अगर कोई और क्वेरी होगी तो आप लोग
sir,
इसके
can you
चैट
give the
बॉक्स
PDF
में।
of this
हाँ
notes?
हाँ,
Can you give the
लव तिवारी बोल रहे हैं ना, बताइए, थोड़ा तेज
Yes,
बोलिए।
sir. Can you give the PDF of this handwritten notes?
यस, यू कैन फाइंड इट, ये मिल जाएगा आपको, और इसका पीडीएफ फॉर्म आपको शेयर कर दिया जाएगा।
अभी ये जो इसका चैट बॉक्स है, चैट बॉक्स में हम लोग अटैच कर देंगे इसकी पीडीएफ या पीपीटी।
ओके सर।
उस पीडीएफ में आप जो सर्किट्स छूट गए हैं, समिंग एम्पलीफायर, सबट्रैक्टर, इंटीग्रेटर, डिफरेंशिएटर, उनका भी कंटेंट आपको मिल जाएगा।
जी सर, थैंक यू सर।
अगर हम लोग ये मीटिंग एंड भी कर देते हैं तो भी
जी
आप
सर।
छोड़िएगा नहीं। अगर आपको पीपीटी चाहिए तो 5-6 मिनट लगेगा सब पेन ड्राइव को। हाँ, तो we'll upload it on chat box. Okay.
थैंक यू सर, थैंक
Anyone else?
यू। नो सर।
No, it's no from your side, na? Other
यस
people
सर।
are there. Okay, so I hope everything is clear, and it was a wonderful lecture by Shri Sunil Kumar sir. मनीष कुमार गुप्ता जी कुछ बोल रहे हैं क्या? Okay, so thank you so much, Sunil sir.
थैंक यू, यू टू आल्सो।
And
इट इज माय प्रिविलेज कि आपने मुझे बुलाया एंड मैं कुछ डिलीवर कर सका।
एक्चुअली हमारा प्रयास ये है कि संस्थाओं में और दूरस्थ संस्थाओं में हम प्रयास कर रहे हैं कि कुछ और स्पेशल लेक्चर्स जो आपको समझ लीजिए कि आपके जो कोर्सेज हैं, दोज कोर्सेज आर बीइंग डिलीवर्ड इन योर इंस्टीट्यूट, बट